Okay, so I now swap with the much longer talk by Professor Wu. So I'm now presenting the talk here as uh, topics about why the deep understanding is important to disaster mitigation. Okay, so the simulation here are done by Professor Lin, and I'm Simon Lin. I'm really we're collaborating on many topics, but Professor Lin is really and his team really did all the simulations. Okay, so the question here is that with the advancement of technology, computing powers, and all these softwares like like from MM5 to WRF, and everyone say these are such a sophisticated software. Why we're still having all these disasters again and again? Uh, if we come to think about this, climate change research is something that somehow we already proven to the world, except some exceptions of some world leaders, like the president of start with a letter T. Some people does not believe in it, but I believe that climate change is already now uh, has already has great impact on the decision makers of different levels. Okay, so in other words, the long-term trend is something that everyone seems to take and believe that there, if we don't do something, and in 20 years time, all the scenario talking about 20, talking about the end of century, and the disaster of the unprecedented scale will happen. Okay, I'll show you in the last slide about one of the simulations we did. But so this is our argument is that and weather service tend to be a day-to-day SOP-like of service, standard operation procedures, where people run these packages and then the prediction will be approved by some senior meteorology officers. So apparently there's some gap between the day-to-day in an almost static kind of situation where the the temperature and then the wind speed and the moist, if they were relatively quasi-static, and these predictions seems quite accurate. So this to be there is a gap between the day-to-day operation and then the long-range climate change. So there was somewhere in between where the deep understanding we argue is important. You have to understand the mechanism behind. So by understanding the mechanism behind, then you look all the prediction in a much broader scale. So I'm going to show some of the examples here, which is about the usually rated with what we call the meso scale. Okay, so you have this weather prediction on area, and then you have these ensembles and then averages on the greater scale. But then not just on the temporary scale, but also on the geological scale, where geographical scale, where the region is also important. Okay, so so rationale here, just like I said, on the practical side, disaster mitigation tends to just focus on worst case, which is all right because you wanted to warn the public the best scenario. But often that most public are not warned, even in the most advanced country like Texas, that worst possible scenario was not predicted. So there were a lot of reasons behind all this. So why the disasters cannot be foreseen in a better way than what we have now today. Okay, so obviously this is, of course, this is not the most optimized way if you only calculate the most worst case scenarios, and I mean literally you can put danger everywhere, and then you don't have resources to move around and to mitigate the disaster, for example. So had we predict the disaster more accurately, and of course society as a whole could be better protected. And we know that the classical problem of this weather system is that it is inherent a nonlinear system, where even a lot of early cases of chaos are rooted in the meteorological systems, for example. And I think the big issue now we all realize now is the coupling between, say, the different systems like the air and the ocean. These are the issues that we haven't been able to deal with in the best possible way. So I believe that some sort of understanding, especially on the qualitative part, is important, and that will be useful to us. So we take the disaster, you take it from 1950 to 2011, okay? Obviously, the number of disaster rises, okay? This is the Munich reassurance label. What's important is that if you look at the, obviously, nature hazard will hamper the sustainable economy, okay? If we have one. So look at the type of this disaster here. I mean, you look at the geophysical one is actually on a relatively smaller scale compared to others. Ironically enough, that the earthquake are much more difficult to predict, and but still, I mean, it causes a less problem. But this is on average scale because the most of numbers of earthquake happens on our part of the world, on the Pacific Rim Northwest side, or this sort of, they call it ring of fires. Okay, so it happens in other places. I mean, China it doesn't happen as often as on the Pacific Rim, but it happens in the way that when the India Australia tectonic plate pushes China and then causes all these long distance effect. And these are the issues, and we just have one recent here, for example. But you can see that most of them related, we say, meteorological events, hydrological events, and of course, the here was classified as climatology events, and these are related with most of the air system and then with the oceans. So in other words, water and the earth are the biggest source of the problem now for the moment. So if time allows, I'll just say a few words. But anyway, I'll try to be because for the sake of time, I will just try to pinpoint. Maybe I'll skip a few slides of what was the qualitative understanding, for example. Suited a typhoon to go to Taiwan in 1915. Okay, these are of course the tropical cyclones. You can see that we still have more, on our part of the world than the Americans, even if they have a quite devastating one recently. Okay, all right. So as you can see, this is the area that we have to study to have better understanding here. So this is average count of increases, yes, but not in a great way. But we know, I think this is already well established in climatology research, that the future warning and typhoon, the scale will be much more increased. In other words, the fluctuation will increase. So typhoon will become more fierce and more damaging. Okay, even if number of increase will not be that dramatic, but then its effect will be much more effective. For example, so damaging. Yeah. So taking the flood in Taiwan 2015, only 2 years ago, the Suda typhoon. Okay, the tricky thing here is that this is the storm track predictions. You can see that actually there was different sources and quite different prediction in the beginning, but it ends up. So this is a huge typhoon, as you can see, very clear eye there. And so this is the effect. Okay, I mean, I just have to show you the slide to see the effect. For example, flooded many places. Yeah. The biggest problem is that you get a very, very weird, kind of in a crooked route of the typhoon. See, that makes a big turn there. Okay. So this is a classical case of the interaction of typhoon with the topographies of a particular space. So, I mean, this doesn't happen all the time. Okay. But we all know the effect of Taiwan, especially to China, is that if the typhoon just came head on to Taiwan, and most of the time it will be largely reduced scale, and it will become relatively less damaging. For example, when it goes to Taiwan, because the highest peak of Taiwan, I mean, Taiwan is central alpine, on average is about 3,000, 4,000 meters. So that's a very, it's usually about half of the height of the typhoon, and that is called the we're going to kill it. So this time is a particular case of the interaction with the topography. Okay, am I going to go? Yeah. So, right. So I think I can risk. We all know that the initial condition and boundary conditions and resolution, these are the most important factors to predict typhoon. And the softwares are actually very mature. So the rule of thumb here is that if you can keep on several conditions, you keep on feeding the most up-to-date data. Actually, one can be quite confident to say that you can predict the track of any typhoon at least before 48 hours. So in other words, that but we make mistake. A lot of senior meteorological officers, because of experience, they make the prediction and they don't believe in computer simulations. Actually, throughout the years of simulation that Professor Lin has been doing, uh, actually we're quite confident to say that if you give in enough computing power, high enough resolutions, and then enough data that can keep on feeding, the typhoon track can very confidently say can be predicted 48 hours before landing. So 48 hours is a lot of warning time, really, in order to move around your resources, etc. And but of course, so this mesoscale wind and prediction, all these are becoming possible with the more increasing computing power. But still, so this is an example. You take a originally the direction was really a different one. This is original prediction on I think the 4th of August and 2/5. So if you look at this one, and you see that actually only 7th is already very accurate, and London is only about two. I mean, here is accurate already. You see that the direction now being changes. So you think about this a small island, and then the landing position, maybe 20 or 30 kilometers away, will cause totally different effect, especially interaction with the topography. Taiwan has very complex terrain. So if landed on Taitung or landed in Hualien, the effect is very different. Or a little bit north, and then the northern part, southern part will be affected different. Okay, so this is one thing. Of course, the bigger problem is the air pressure and wind speed. These are much more difficult to predict. And all the accuracy of the wind speed and the air pressure actually relies on the continual sources of data. So of course, data is important. You need a convention, boundary convention, and then data. And data this shows the value of data, because if you can, the data can be keep on, updated. You're talking about maybe 100,000 people's wealth, or even hundreds of people's life will depend on it. So this is something that science actually relates directly to the natural disasters, and this is something we cannot ignore. And of course, experience show, because not everyone is expert on this field. Just kind of give you some background that the typhoon track is relatively easy to predict, and the accuracies of the air pressure and wind speed actually relies very much on data. So I'm going to show you another case later on that because of the loss of data somehow. Anyway, we should. Okay. So the other one is flooding in Sri Lanka, 2016. Okay. I mean, this paper have been published, but just this again is effect. Actually, it's actually quite devastating. Total numbers of people affected are close to 500,000, and 100 dead and 100 missing due to landslide. So what happened? Okay, so if we take this here, I can just give you the reasons, and they couldn't be predicted accurately. This I'll show you just reason. You see, it's a low pressure. I just show you the picture, then you'll see. So these are the most heavily hit part on there. Okay, and it was no. This is the reason you cannot see the move now. So this is really the it's not a typhoon. It's really just a monsoon coming on. Okay, so but then it converges here. So you can see, because originally it's an animation, so you can see the how the low pressure system come in. So the low pressure system come in, and we actually, this is a convergence zone. Okay, so all right, a little bit of animation. All right, all right. So this actually show you very clearly that you got the westerly wind, and it's a low pressure system comes in, and sometimes actually the prediction has to go beyond. You must have data, for example, the warning of a low pressure coming, and this forms a convergence zone. So the whole two things together and created the flood that was not expected. Okay, this is one reason. So you can see that so heavily here, unbelievable, just on that convergence zone. So this is one thing which you know this is just the paper just been published. That means that it's actually beyond the capacity of the weather bureaus now to be able to see such an event to happen. Okay, so this is something that was. So the other one is storm surge in Philippines. The biggest problem here, I think for time's sake, is that they actually have the LiDAR and also the radar information, but then the radar was destroyed when the typhoon was closed. So they got only 1 day. So that makes all the continuous feeding of data very difficult. That was the situation here in storm surge in the okay. Maybe I should say a few words about the issue here. So it's not just a typhoon. This is similar to what's happening in Harvey in Texas, where the biggest damage actually coming from the storm surge. Storm surge is a phenomenon, especially it's the cause of the typhoon blowing the water surface, and especially the low pressure system of the typhoon that actually will increase the effect, and also the undersea topography was important because that actually it's again it's similar sort of if there's a slope and then the surge on the sea surface is going to be increased because of the slope to approach land, and also the tidal effect. Okay, so these three things come together and it will create this was unprecedented. Actually, the storm can move in to 500 meters. Of course, the tsunami can move even deeper, but then this is really where the effect happens. So we had problem with the I mean track is easy. We can reproduce the data and track is very accurate. So for a while we couldn't get the air pressure right, and then couldn't get the wind speed to be high enough to what some of observed data at home. But I think recently we make progress on this area that we are being able to improving the predictions of typhoon much better itself. So I think you can even tomorrow at this home. I mean, with our I mean we're expert here. They're working on some searches and with the companies to resolve, and then I think this might be the most accurate simulations of the typhoon of the high-end typhoon in Philippines. Okay, this is one of the events being used, and I believe that UNESCO is also putting attention to especially the rescue part. And so these are areas that was affected. I think just so some measurement and simulation, but I think this Dr. Tai and Professor Wu has a better result here. The other one is flooding in Malaysia. This again is an issue that was ignored. This was happened in 2014 to 2015. Okay, the result of the flooding in Malaysia. It's actually not a single event. It's a continuous about 20 days of events happening in that area. 20 days. Yeah, it's from the Christmas to the beginning of January. Okay, so it's just from 2014 to 2015. Okay, I think this is the. Maybe I'll use 10 more minutes. Yeah. So this one, the 15th of December and to the 3rd. So this is about 20 days effect. So the biggest effect here is what I'll show you the result. So this is the change. It's what they call, it's called Borneo vortex. So Borneo vortex is something that was actually been discovered in 1987. So this is supposed to be known, okay, but still causes such effect. It's the motions or of the Borneo vortex move around between the Borneo and then the eastern Malaysia. This is the biggest cause. So of course the weatherman should pay attention to this thing and then try to see or try to use. Sometimes difficult to see. Maybe sometimes satellite information will be useful, and try to watch over that and see the approach, and you're going to get a much better understanding of the disaster having happened. Okay, so I think that just because of it's just originally was PowerPoint become Keynote, and then some of the characters went wrong. So I think I'll say a few words about the environmental research topics. Okay, This is already known, but not that well, which are the long-range transport of air pollution to Taiwan. Why use Taiwan? Because you look at the position here. Taiwan it's actually just in the middle. So it's no surprise that during the winter time, when the air system on the continent is stronger, it'll move down, right? And then the Pacific, the ocean air system is weaker. So I mean, something's going to brew from Siberia, Mongolia, all northern part of China down to Taiwan. It's inevitable because that's just weather. That's the conditions, for example. But it was really well known that even the biomass burning here in Indonesia is going to be to affect there. Important is that this shows this impact biomass burning pollutant for Indonesia. So this just shows the importance of mesoscale simulations. Okay, so so this was the forest fire when it was seen from satellite. It was the those material that the pollutant went to the air, and then you can see the why it doesn't move. Okay, sorry, so this slow here. Okay. Oh, don't move. Okay, I cannot. Okay. So the first one is, of course, from the pollutant from the north. So we can see here. So these are the yeah. Can you see the simulation? Maybe yeah. So this is how they move. Actually, usually several thousand kilometers. Okay, for north, and this was done by Wolfcam because this is effective. The Wolfcam, particularly, that can deal with pollutant quite effectively. So it can deal with the result of the dust, and then some of it's the agents of the dust and the component how it interact, and they use diffusive mode. So the diffusive of the diffusion of the chemical reaction, and then get transported by the air system. Okay. So actually the other one. Okay. So all these are just being published recently. So, all right. The other one is okay, this is the most interesting. This is not about the air system. But then what is this? It's because in southern part of China and also northern part of Indochina, there are mountains. And mountains create with, especially some of the low altitude uplifting stream on northern part. So it create what they call the Lee Trout effect. Okay, so the pollutant in the Indochina get lifted and then transported, and with the direction of the monsoon or the season wind, it's actually brought to the east. And actually, I skipped that slide where the measurement in top mountains in Yushan actually on the forest fire. So this is one of the important results that's actually demonstrated that the whole region can live together somehow. This is something which is unavoidable, that the phenomenon happen in thousands of kilometers away. Even it's an air phenomenon, it will affect you if it's the right condition. Okay. Okay, so these are of course, the haze was something people can see immediately, but they didn't know that the long-term and long-distance effect to other parts of the world. Okay, so these are the result of these are the pictures from the Southeast Asia haze in 2015. Okay, so some of them. I'll just show you the other one. So this is the simulation of the. Usually they're okay, but in the springtime, the forest fire. I mean, usually if you look from the satellite, on the orders of 30 or 40,000 spot of the forest fire in Indochina. So you can see the effect. It's not just Indonesia, but also in other parts of the Indochina. Okay, so these are simulations. Okay, the other thing I would say is this is some of the research we did. I think these are much more of. I think this is important. It's of historical importance. So if I explain to you, if I can choose this, you see, Taiwan is a long island, and then on the western part, it's a relatively narrow plains, which are usually so the air pattern, obviously, from the basic meteorology is that it composed of several parts. One is ocean, and the other is plainland, and the other thing is island. I'm sorry, mountains. So Taiwan is lucky that 2/3 of land mountains cannot be used. I think that's a blessing rather than because especially if you look for the future, this is really a blessing. You take the specific heat of the ocean and the plain and mountains. It just comes in descending orders. Okay, so ocean has the biggest heat specific heat or heat capacities, and the next is plain and then the green. The Greenland or the mountains are covered by these trees, and they actually has even smaller heat capacity. So because of that, the motion of the sea breeze and the land breeze actually is a natural phenomenon, and that was the weather regulators, if you like, for the past 100 years. But something had changed. So if you look at time, the temp. I'm sorry, did I give? If you take the histories of Taiwan is that luckily we have the meteorological observatories, some data from 1895 uh, during the Japanese period. So that was some of the data that's very useful for us to study. The first question we asked was, in how many years? I'm talking last century. The rise of the temperature is something like between 0.6 to maybe 1 centigrade. That's a lot already. But why in Taiwan, in many parts of the world, the rise of temperature is 1.6 average? In some, I'm not talking about all, but then especially for that part of the world. What was the reason? So this is what we did. I think this is one of the most, this is kind of very interdisciplinary. Eric, in the old days, in 90s, he helped to lead digitizations of a Japanese map was drawn in about 1904. So it's called there were two set of maps. One is the Taiwan topology one, so they're very accurate ISO scale height maps. So you know where all the topographies and in those days because it could change. And the second one is very interesting. It's what they call the village map. I don't think it was what Baotu. Village map is interesting is that they actually draw the maps on the usage of land use. So this is a farm, and there's a village and a city, and there was etc. buildings. So that turns out to be very useful clues that we can understand the changes of weather. So Eric lead a team that actually digitized that map in about 1997 or something. Yeah. So we had that data very, very valuable. So we take 1904 and the 1921. There's two period under the Japanese period, and then the 1994 and 2007 period. Okay. So because of the land use data that can give you a quite confident way to estimate the potential impact to the weather, because there was a there was empirical formulas for that. So we take that and we take one day I think it's in about that time, but a very typical day is important, and then you take the global weather, take the global model and reduce it down to the coastal Taiwan area. So in other words, you take a typical day and you want to see the effect of land use of 4 period. Okay. And I'll just end up with the result. I think I'll just very quickly show you that basically in some area, every temperature rises by 2 centigrade. That's a lot. 2 centigrade is a lot. Okay. I think more, I would just, let me just, okay, this is more important is that, in the daytime, the sea breeze came in. At night, the land breeze brought the heat out to the sea. On that part in Tainan, it's the southern part, it's now called Taijiang Neihai. The land breeze delayed for 1 hour. What does that imply? That means the effect of the regulator, the effect of the air system that can propel out the heat, the effect has started 1 hour later. So that means it's become less effective to be able to get the heat out. Okay, that's one thing. Okay, and I think I'll just say the result. So there's a lot of different result, and then it's okay. This is just show the changes. But anyway, I'll tell you the second one. Okay. Well, so the first one is average temperature on that part of the world increased by 2 centigrade. The second one is that basically in most of part the sea breeze was delayed for around 1 hour. Okay, and also okay, I think if this is the incomparability of the format I just said. Okay, I think can I okay let me just okay. So and the other thing which was very important is that the usually in the afternoon there's a convection rain near the mountains, okay, but because of this the distribution uneven distribution of the heat, the all this convection moved to the west. So what happened now is that the water reservoir on the mountains cannot collect enough water, and then the city get too much rain and cause the flood. This is very typical of those scenarios. You see, I after result I went to present. I got the National Science Council the support of this grant and report result. And because of division of labor, so we reported to actually to the urban planners and asked them, have you thought about this? They didn't. They think about land use. They didn't think about this potential hazard that might cause by the human activities. But none of these have been included on our urban planning, on the planning of nation. How do you plan this area? How are you going to move people around or to make them a livable place where that you can have low risk of disaster. This is not in the blueprint or in lands of the because it's a limit of discipline. They never thought that way. They think oh it's this kind of human activity in the last 100 years. It's already changed our landscape. Okay. The other thing I think I'll just show you the result here. Okay. I think I'm using a lot of time. Sorry. I hope there's still coffee left. I'll show you. Okay. I'll end it with this one. Okay. This is very interesting. Remember the Moron typhoon, which is again it's a historical thing. It's maybe the third highest precipitations. So in 3 days, they were 3 meters away. Okay, it's more than in the Harvey in Texas. And one of the effect is that it actually get rid of because the water comes so fast. It's whole the hills was washed out. So about 500 people was buried. I think someone might remember that. That was unacceptable. But you know, it's a hill, and in a few hours time, the whole hill was gone. Okay, there's people living in the hill. So there's one if this type of Morocco and it's happened in the end of 20th century, what will happen? The simulation result shows that the precipitation, the water will be rain will not be just 3 meters, it will be 4.2 meters. Think about how the devastating effect will be. Okay, so I think computer simulation, all these things are very useful, but if if you see cleverly and we use it right way, we're going to see a lot of insight and going to change our mind of planning the use of land and how do we live and how do we prevent the disasters. I think these are very important. So qualitative understanding is such an important issue, but because of the expert and also the people who are in the operational weather predictions, that this is just the gap which is missing, that we should spending more effort on that and try to help each other to have a better understanding of issues. All these issues about the differential equation, about initial condition, boundary condition, and data is something that is still not sufficient. Okay, and observation data could easily get destroyed after the onset of major disaster events. Okay, I emphasize about importance of mesoscale. Mesoscale should be something which is on the you know on the mind of the operational weather person. They should